Let's start with a function. Here, I've graphed y equals sine of x. And what I'm going to do with this is I'm going to calculate an integral. So I would like to look at the integral of the function f of x equals sine of x, starting at 0. But then I'm going to end my integration at the number a. What number is a? I'll choose it as I go. Now I've set up this graph to illustrate, how much area am I looking at for this definite integral. For a equals 0, of course, integrating a function between 0 and 0 gives me 0. There's no width, so there's no area. And I can move this slider out a bit. Here I've highlighted some areas going from 0 to 1.9. And actually Desmos has gone ahead and calculated this integral for me. So I know that if I was going to calculate this myself, I would use my antiderivative. The antiderivative for the sine of x is minus the cosine of x. And I can use my evaluation formula to calculate this. The further I go out, right, as I change my value of a, I get different numbers, right? The value of my integral changes. So by varying my stopping coordinate, I get different outputs. I get different amounts of area. Here you can see below the x-axis, my area is negative and it takes away from the integral. Then above the x-axis again, my area is positive and it adds to the integral, and so on. But the key thing for today is this idea that I can use an integral formula to define a function. So I started off with this sine function, and I'm going to say that my new function, g of, let's say, a, and my input variable will be a for this problem. This is the integral from 0 up to a of sine of a all, sine of x all dx. So even though an integral is a fairly complicated thing, an integral is a set of instructions for calculating a number. Different value of a, different number is my output. So this really is a function. Maybe we'd feel a little bit more comfortable about this if I wrote this as using the evaluation theorem. So I'd say to calculate this integral, I'd have minus the cosine of x evaluated at the two different coordinates, a and 0. So it looks to be, what have I got? 1 plus cosine of a after I do my double negative. Actually, let's go ahead and write this all out. So I have minus cosine of a. Yes, I did mess up the double negative. Good to check that. Minus cosine of a minus cosine of 0, but that's the double negative. Cosine of 0 is 1. So this formula just gave me a more complicated way of calculating 1 minus cosine of a. Now, in general, I'd like to be able to study this kind of function, this kind of g of a, where I am defining a new function off of starting an integral at some coordinate and then varying the stop place. So if I think about it, how would I calculate the derivative of this thing? I've got my g of a function, the same as I was just describing. And one of the perspectives we learn in this class is that we can better understand a complicated function by looking at its derivative. So how am I going to do that? Well, I know that I'm supposed to look at the limit of g, make some more room for that. The limit of g of a plus h minus g of a all divided by h. I'm taking the limit as h goes to 0. What does that actually look like for my graph here? If I integrate from x equals 0 up to x equals a, and then go just a little bit further, what have I got? Well, here I've stopped at a. My a is, let's just make that 7 to make that a little bit easier to see. And I'm going to go out just a little pinch further, like this. Now, I've chosen a value of h that's pretty small here. I will need to zoom in some more. So maybe you can start to see some purple here. Let me stretch this a little bit. So let's say x goes from 6.999 up to 7.0001. Oh. That's a little bit easier to see. So what I've got here in purple, my h here is, what number is that? It is 1/100th, or 0.01. So how much more am I adding on here? Well, as I take smaller values of h, right, this rectangle here, or almost a rectangle, I can see that's not quite a horizontal line for the top of that. This purple region is going to be, well, I've got a width here. The width is h, and my height here depends on the function I am integrating. So this height here comes from the sine function, we'll say evaluated at 7. The width here is h. This purple area is representing the change in my integral. So here I've taken the integral all the way up to 7.01, and I've subtracted off what's in blue here, the integral only stopping at 7. So this limit that I'm looking at is almost sine of 7 is the height, h is the width. Huh. If I've got an h on the numerator and an h on the denominator, those are going to cancel each other. So this change is approximately the value of the function that I have inside the integral. So this is a really interesting thing and very important too for studying functions and studying integrals. So again, what this is saying, if I have an integral, and on the slide they use slightly different letters than what I was looking at. So integral starting at any point that you like, we'll call that A, finishing at the coordinate x. We're integrating the function f of t dt. We do need a dummy variable here. We can't integrate something up to itself. If if x is a variable, I get different outputs from this formula, which defines a function. And so I'm going to call that function g of x. So you can imagine this x, as it moves to the left and the right, I get maybe more or less area. And this result that I've been talking about here is part of the fundamental theorem of calculus. This is one of the most important things about how calculus works, that we can define these integrals. We can use them to build up this area function. And so long as the function f that we started with is continuous on the interval, say from a up to b, then the area function is, well, first of all, it's going to exist. We are able to define this thing. It's continuous, that's nice. But also, this area function is itself differentiable, and the derivative of the area function is my integrand, my f of t. So g prime of x will be f evaluated at x. So what this is saying, okay, there's a lot going on in this theorem. What this is saying is that taking the derivative of an area function undoes the integral. So if I'm thinking about integration is measuring how much area I accumulate, and then I look at how quickly does that change, those two processes cancel each other out. So it should make sense that my area function grows faster when my function that I'm integrating has a very large y value. It should increase slowly if the y value of my integrand is small, or it could even decrease if the y value of my integrand is negative. So the rate of change of my area function is completely determined by the graph of my integrand. Now, it might seem a little hokey to even work with these area functions, but depending on what your major is, they actually do come up in a lot of different circumstances. Lots of important functions come to us not with a nice clean formula, but with something involving integrals. And what those will look like will be slightly different depending on what your major is. But now, if you do see something like this in the wild, we know how to integrate it. So if you have a function like this, say s of x is the integral starting from 0 and going up to x, and we are integrating sine of pi times t squared on 2. Well, we can try to graph that out. Maybe we'd get a shape something like this. But if we're going to think about its derivative, how quickly this changes, Well, calculating this derivative is no sweat. The derivative of this function is just the integrand itself. Now, this goes hand in hand with the way that we have been evaluating integrals. So we talked about how antiderivatives allow us to calculate definite integrals as long as f is a continuous function. If we know its antiderivative, the integral of f is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So you can think about this. Let's say that we know lowercase f is the derivative of some function. Well, I can undo that derivative by taking an integral. So derivatives undo integrals, but also integrals undo derivatives. So each of these things undoes the other. We like to think of these as two parts of the same formula, two parts of the same result, because they're telling us very important information about these sort of two different things we've been looking at in calculus: derivatives and integrals. Or you might talk about derivatives and antiderivatives. So one way we can think about this, if I take the derivative after integrating, I just get the function that I care about. And for definite integrals, if I integrate a derivative, I can evaluate that by this difference here. So an important technicality of this is that the fundamental theorem of calculus part 1 gives us an answer that is a function. I have an area function and I calculate its derivative, which is some other function, f of x. And it's important that this function actually matches the integrand that I started out with. If I go the other way, if I take a derivative first and then calculate a definite integral, like in part 2, this is giving me a specific number, because a definite integral tells me a number. It tells me the net area between the graph of the function and the x-axis. And it's useful to know that the calculation involves the original function itself. But it's also important to note that in this context, I get a number, not a function, as the result of my calculation. Now, this idea is going to lead towards the idea of an indefinite integral. Why is it that I can undo derivatives, but I've got this, plus c business? Every antiderivative has some constant because we lose constants when we take a derivative. If you don't know what it was to start out with, you're just not going to know what that constant was. So in light of the fundamental theorem of calculus, antiderivatives, we can calculate these things using definite integrals. And this leads up to the idea of an indefinite